Hi, and welcome to lesson 14.1. We're talking about rational numbers and irrational numbers. And within this, we got to know our essential question: how do you write or rewrite rational numbers in decimals to take square roots and cube roots and approximate irrational numbers? Well, let's find out. Well, first off, uh, we need to know what is a rational number. So a rational number is any number that can be written as a ratio of the form a over b, where a and b are integers and b is not 0. Examples are this. So let me slow this down a little bit. So it's a fraction of integers, basically. So, see, 6 is a rational number because it can be written as a ratio of integers. Integers, if you remember, are the positive and negative whole numbers, such as if I have a line here, 0, 1, 2, -1, -2, these are integers. Okay, so you pick two integers like this one, and you go -2 over 1, and voila, you have a rational number. So that's what this is all about. So if we take 0.5, that can be written as 1/2. And 1 is an integer, so is 2. All right, enough about that. Every rational number can be written as a terminating decimal or a repeating decimal. So terminating decimal is such as 0.5, and it terminates or it comes to an end. It has a finite number of digits. A repeating decimal is a block of one or more digits that repeats indefinitely. So let's look at this. Turning these fractions into decimals, you just divide. 1 divided by 4 is 0.25. And this is a terminating decimal right there. And for this one, 1/3 is a repeating decimal. 1 over 3, divide that, and it's 0.3, and the 3 just repeats. And we put that bar over it when it repeats. Okay, so moving on let me find my other page here. Here it is. So your job at this point is to write each fraction as a decimal. So you go ahead and divide the top number divided by the bottom number, and pause the video at this point and see if you can figure out what these are before I reveal the answers. All right, the answer to the first one is 0.45, and the 4/5 repeats. 4/5, 4/5, 4/5. The 1 divided by 8, that is 0.125. That's a terminating decimal. And 2 and 1/3, that is, oops, I don't want to get rid of it. There we go. 2.3, and the 3 repeats. So there you go. Let's see what else we got. So next, we're expressing decimals as rational numbers. So we're going the other way. You have the decimal, and you try to create or turn it into a fraction, essentially, because if when they say make it a make it a fraction, simplest term right here. So we could take this, and this, I mean, if you look at that, yeah, we often read that as 0.825, but really the 5 is in the thousandths place there. So we call that 825 over 1,000. And then you just simplify that. 25 will divide each of those, and you get 33 out of 40, and that is the simplified form. Now, this here is a little bit tricky in this part here. So we have this 0.37. 37 is repeating. And I'll tell you right now, the quick way to remember this is if you have 0.37 with a bar, that is 37 over 99. But if you have 0.37 without the bar, that's 37 hundredths, or 37 over 100. Okay, bar, you got nines. No bar, it's over 10, or some kind of power of 10. And you might be wondering the reason why. Well, here is the explanation. It is not an easy explanation, but we go from this here. First, you let it's a very abstract and strange process, but you start with that, and the number has two repeating decimals, so we multiply each side of this little equation here by 100. So we're trying to move the decimal all the way to the right. And so you multiply both sides by 100. 100 times x is 100x, and 0.37 with the bar times 100 means you're going to move the decimal 2 times to the right. Okay, so both sides are multiplied by 100. Now, in the original statement, x is 0.37 with a bar over it. So if we subtract one of those x's, subtract an x here, and that's 99 x's, subtract an x here for 0.37, and all of a sudden these all just drop out, and you have 99x equals 37. Now we're going to solve for x. As we solve for x, we divide both sides by 99, and voila, you get 37 over 99, which is what I originally told you was the whole thing here. Now, you're not asked to do that whole equation that I showed you. You're going to be asked to use it. So knowing this and knowing this, that's all you're going to be asked to do. But this is the behind the scenes. This is the why of what is happening there. And it can be a little confusing. Okay. Now, where was I? Over here. So, what you got is we're gonna now practice, and I want you to pause the video and see if you can get the answer for this one and this one and this one. All right. So, 0.12, that's 12 over 100, or 3 over 25 as a simplified fraction. 0.57, okay, that's 57 over 99, but you can simplify that to get 19 over 33. And 1.4, okay, that's 1 and 4/10, or 1 and 2/5, because 4/10 simplifies to 2/5. All right, finding square roots and cube roots. There's a lot of information here. The square root of a positive number, p, is x squared equals p. There, the square root. I mean, I'd like to say that. Well, here, this is a good example. The square roots of 36 are 6 and -6, because 6 times 6 is 36, and -6 times -6 is 36. That's what this is saying here. The square roots of this of 1/25 are 1/5 and -1/5. So what this is saying, let me bring this over here. So the square root of how about square root of 16 is equal to 4, but it's also equal to -4, because 4 times 4 is 16, and -4 times -4 is also 16. So, and what they're saying over here is the square root of 1 over 25 is equal to 1/5, because 1/5 times 1/5 is equal to 1 over 25. Oh, but it also could be -1/5 also, because a negative times a negative is a positive. That's what's happening with all that. Now, oops. So when they have this here, it looks like I made a bit of a mistake, but the square roots of that are that. So that symbol indicates the positive or principal square root. So we're just going to, so when we have this symbol here, we're just going to talk about the positive square root, not the negative. Number is a perfect square if it has square roots that are integers, like 81 is a perfect square because the square roots are 9 and -9. The cube root means you got 3 numbers that multiply by itself to get to that number. So like 2 cubed is 8, and the cube root, so that means that's the cube root. So if we have the cube root of 8 is equal to 2, because 2 times 2 times 2 is 8. And we have here a number is a perfect cube when it has a cube root for an integer for a cube root, such as the cube root cube root of 27 is equal to 3. So 27 is a perfect cube. So we have these equations here, and they're saying, well, this is saying what is the value of x? What number squared is 121? Well, that's 11. So it could be 11 or negative 11. So it could be 11 because 11 times 11 is 121, and negative 11 times a negative 11 is also 121. And they write this. This is called plus or minus 11. That means you could have the positive or the negative version of that. To take care of this one here, x squared, and we have all this. Well, the square root of 16 is 4, and the square root of 169 is 13. And it could be the positive version or the negative version of it. Okay. Moving along. I'm not going to do that part. I'm going to show you. They have the cube roots now. Now on these cube roots, we have, well, what times itself is 729? What times itself 3 times is 729? And that's 9. Because 9 times 9 times 9 is equal to 729. And when you're doing something like part D here, you would take, well, we need to know the cube root of 8 over 125. So you could take the cube root. You could take the cube root of 8, and you could take the cube root of 125 separately. And the cube root of 8 is 2. The cube root of 125 is 25, because 25 times 25 times 25 is 125. And this is where they're getting that answer right there. Okay, so pause the video and see if you can come up with the answers to these 4 questions. Okay, so what times itself is 196? I believe that's 14. It could be positive 14 or negative 14, so that's plus or minus 14. Number 8, what times itself is 9? Well, I could tell you this, you do them separately. We need to know the square root of 9 and the square root of 256. You do them separately. 3 times 3 is 9. And I think 16 times 16, I think. Let's find out. Yeah, that's it. So plus or minus 3/16. What times itself, what we're looking for is on this one, this cube root of 512. What times itself 3 times is 512? That should be 8. Oops. Let's try that again. That should be 8. Good. And then what times it's, so separately I would take the cube root of 64 and the cube root of 343. The cube root of 64 is 4. 4 times 4 times 4 is 64, and 7 times 7 times 7 is 343. And that's what we should have here. 4 sevens. Okay. And okay, so the final part here is we're going to be estimating irrational numbers. So irrational numbers are kind of the opposite of rational numbers. So they can't be expressed as a fraction. Or, as a fraction of integers, or they're not decimals that repeat or terminate. So we're going to estimate the square root of 2. Because first off, what is the square root of 2? What times itself is 2? Nothing I could think of. So it's irrational. And to find out something close to it, you find 2 consecutive perfect squares that 2 is in between. Well, the square root of 2 should be in between the square root of 1 and the square root of 4. And I picked those two because the square root of 1 is 1 and the square root of 4 is 2. So that's what that should be. and 2. Yeah. Okay. Then we have the last part. Wait, where'd it go? Right here. We have the last part here. We're going to estimate that. So it's in between 1 and 2. Yeah, it's in between 1 and 2. So we could say, well, what's in between 1 and 2? 1.5 is in between 1 and 2. And to find a better estimate, we would choose some number between 1 and 2 and square them. So there's a couple numbers in between 1 and 2, like 1.3 is in between those two, and 1.4 is, and 1.5 is in between those two. And when we square those, we get 1.69, and 1.96, and 2.25. So the square root of 2 is in between 1 and 1.3 and 1.4. And how do we know? Well, or is it? And how do we know? Because 2 is not in between 1.9. See, what we're looking for is that square root of 2, and 2 rests in here. 2 is not in between those two. So yeah, it's in between 1.4 and 1.5. So then, is it between 1.4 and 1.5? Yeah, I think I just said that. Hello. Yeah. And 2 is closer. So now, 2 is closer to what? Is it closer to 1.9? Is 2 closer to 1.4, or is it closer to 1.5? And I think it's closer to 1.4 because this is closer to 2 than that is. So we have it's closer to 1.96 than to 2.25. So the square root of 2 is somewhere around 1.4? 1.41 maybe? Pretty darn close to 1.4. Yeah. And we have this stuff here. Square root of 2 is about 1.4. And let's see here. So how would you find an even better estimate of that? Well, you got to just go in closer. And you test the squares, the numbers between 1.4 and 1.5. And that's what was happening here. So you test those squares. So in between 1.4 and 1.5. All of these numbers are in between 1.4 and 1.5. And so we're just getting closer to that. So square that one, square this one, and square this one. And we can see here, this is going over 2 right here. So 2 is closer to 1.41, I would say, than this one. Oh, that one's pretty darn close. They're all really close. So it's closer to that one than to that one because this is closer to 2 than that is closer to 2. So the square root of 2 is going to be about 1.41. And to get that decimal, you just keep on doing that. It's an exhaustive exercise. And we have a little graphic here. It's about 1.41. And we have all these numbers here. So there it is. And write your answer as a radical expression. Express this. So try this now. Say what you think the square root of 7 is. And so the square root of 7, I would pick the square root of 4 is underneath that, which is 2, and the square root of 9, which is 3. So what do? You test like 2.4, something like that, 2.5, and you start testing it just like the process was ahead. Pause the video and try to get 2 decimal places to the square root of 7. Well, if you did it, this is what you got. Ooh, 2.6. So it's about 2.6. That's what you get. And so these are the ideas behind rational and irrational numbers. I hope this has been helpful. Thanks for watching.